T-minus 10, 9, 8, 7, 6, 5. All three engines up and burning. 2, 1, 0, and liftoff.
Today on Citizens of Tech, we interview Dr. Patrick McCarthy, interim president of the Giant Magellan Telescope Observatory. The GMT project is in its early days, but promises to be the largest telescope in the world once it's operational. And Dr. McCarthy, I guess we're going to call you Pat for the show here. Welcome to Citizens of Tech, and if you would, please introduce yourself and tell the folks what you do.
Sure. As you said, my name is Patrick McCarthy. I'm the project director and the interim president for the Giant Magellan Telescope. I'm an astronomer by training, but my job here at GMT is to help define the scientific mission and manage the overall organization to ensure that when we build the telescope, it actually is capable of doing the science that we've set out to do.
So let me hit you right in the beginning here with why another telescope? I mean, we have a lot of telescopes out there, so what is the GMT bringing that we haven't had before?
Astronomers want two things from telescopes. The first thing we always want is more light. The universe is huge. It's unbelievably huge. And so the distances to stars or galaxies is so vast that only the tiniest fraction of the light from them actually makes it to the Earth, and from that, only a tiny fraction falls into our telescopes. So if we want to explore the universe, we need to collect as much light as we can. So it's been a constant quest since the time of Galileo to build larger and larger telescopes just because they collect more light, and that allows us to see things that are fainter or in greater detail. The other aspect of a telescope, though, is we want to see those sharp details. We want to get a magnified picture of distant objects, galaxies, stars, people across the street, whatever it is that you're looking at through your telescope. And your ability to see fine details, your angular resolution, is determined by the aperture, by the diameter of the telescope. So we want to make a telescope that's larger to collect more light and to see finer detail. And that finer detail really is coming into play now in a big way when we want to think about looking at planets around nearby stars, or the environments in black holes, or the structures of galaxies when the universe was young. So there's a huge amount that we don't know about the universe. Telescopes are our vehicle for discovery, and their power just goes as their size. So in some sense, for astronomers, enough is never enough.
So, right. So larger than ever before is for good reason. We need to be able to gather more light to see what we haven't been able to see before, and that's one of the things we're getting here.
Absolutely.
Well, okay. Now, you mentioned some goals, gave some illustrations of what we'll be able to see with the GMT. Okay. Can you give us some more? Maybe dive into that a bit. As I was doing my homework on this for this show, distant galaxy observation came up. In other words, getting us closer to the Big Bang, observing planets orbiting nearby stars, maybe. Maybe we could identify planets with the chemical signatures of life. Are these all possibilities?
Absolutely. But first, it's worthwhile to step back and think about the big picture and why we do astronomy, why we build telescopes. And it's primarily to understand what's out there in the universe and to discover new things and learn mostly what we don't know and things that we believe we know now that turn out to be wrong. And there's a great quote that when George Ellery Hale went to the board of the Rockefeller Foundation to ask for money for what became the Palomar 200-inch telescope. The board said to Mr. Hale, he said, "Well, young man, tell us what you'll discover with this giant telescope." And he said, "If I knew that, I wouldn't need to build it." So really, we build telescopes to discover new things, to let the universe tell us what's out there. And what we've learned over the 400 years since Galileo is the universe is vastly more diverse and rich and complex than we ever expected. And so we always bear in mind that discovery space, new potential, is our primary driver. But we have to have a plan. We have to have things that we wish to observe that we can use to fine-tune our engineering, to develop the telescope to make sure that it can do the basic things that we want to do. And right now, it's a very special time to be in astronomy, in that we're undergoing a revolution in our understanding of planets around other stars. And we're at a special time that we can look back to almost the very beginning, just very shortly after the Big Bang, to see the genesis of the first stars, galaxies, and black holes. So let's take those two topics in order. We'll talk about the neighborhood. So in my view, the first thing we want to do with GMT is meet the neighbors, understand where we live, what a typical planetary system is like, whether our solar system is normal or unusual. So we now know that planets are ubiquitous around stars in the Milky Way. most stars have planetary systems, or at least a good fraction of them, and that planets that are a few times larger than the size of the Earth and in orbits are anywhere from, say, that of Mercury to the Earth are quite common. But what we don't know much about them is what's their structure, what are their densities, do they have atmospheres, do they have liquid water, do they have conditions that are conducive to life? And the amazing thing is, when I was a young person going to high school or even to college, those are things that we would call science fiction topics. There was no even thought that we could address those as scientific questions. But now we have the tools to measure the physical properties of planets around other stars, to deduce their chemical composition, their structure, their densities. But we are really limited in the ability of our tools that we have now. And it's primarily an issue of angular resolution and to some degree sensitivity. So what the GMT will do is allow us to see details that are about a factor of 10 sharper than we can do now. That will allow us to see planets around other stars. And the reason this is challenging is if you were, say, living in Alpha Centauri, or perhaps if you lived on Proxima Centauri b, the planet that was just announced this week, and you looked back at the solar system, the Earth would be so close to the sun that it would be less than, or just about 1 second of arc away from the sun, about 3/4 of a second of arc. But it would only reflect 1 part in a billion of the sun's light. So it'd be very hard to see, very hard to separate it. But with the GMT, we can do that. And in fact, we can then do the reverse. We can look out and image Proxima Centauri b and separate it from the light of the star itself. And that way, then we can look at its colors, its composition, its motion, and ideally this question, does it have an atmosphere? Because the atmosphere is not only essential to life, it provides some of the tracers and signatures, or the evidence of life. So if you look at them, maybe we should just stop there and pause, and then we'll carry on as needed.
Actually, it's perfect that you mentioned Proxima Centauri b, because that was my next question. Will the GMT help us, detect whether there's water and an atmosphere and things of that nature? And you basically answered that, I believe. It sounds like it's at least going to help in some regard. We're not going to be able to look at it like we can look at Saturn.
Right. Well, we certainly, one of the most exciting things about this recent discovery is it's a rocky planet in an orbit in which water is likely to be liquid, and the GMT and similar telescopes that are being planned elsewhere in the world will have the angular resolving power to separate that light from the star. Telescopes today, I don't think, can quite do that, but the GMT will do that, and it'll do it well. Okay. The question then of water and atmospheres, that gets a little trickier in the sense that some of those measurements are best done when the planet passes in front of its star. And I don't think we know yet for Proxima Centauri b whether or not it transits in front of its star. You have to get lucky. You need just the right geometry. You need to be kind of lined up in the plane of the orbit of the planet to see it go in front of the star. And my guess is a priori, it's unlikely that Proxima Centauri b is one of those. But one of the neat things about this recent discovery is it's a planet around what we call a red dwarf, or an M dwarf star. It's a star that's only about 15% of the mass of the sun. It's quite a bit cooler, but those stars are the most common stars in the Milky Way. If you just did a sort of a survey around the neighborhood, you'd find that most of the nearby stars are these dwarf stars. That's where we want to look for additional planets, and some of them will surely pass in front of their stars.
Now, you mentioned the degree of fine detail that we can get when the GMT goes live. But it's Earth-based. Isn't there some amount of compromise that happens because we're looking through the atmosphere of the Earth into space as opposed to a space-based telescope?
Yes, there is that detail that we neglected to mention, and you raise an important point, because for the history of astronomy since Galileo first built his telescope that was just a couple inches across, once we got to apertures that were bigger than about 20 inches or so, the angular resolution no longer increased because we're looking through a turbulent atmosphere that has different temperature cells, it has different turbulent cells, and we've all seen this when you go outside, particularly on a summer day, and look across, across hot pavement, say on the interstate or just on a city street. You see all the images shimmer. That still happens when you look straight up at the stars. That's why they twinkle. One of the great advances in ground-based astronomy over the past about 30 years, but mostly in the past 10 years, is our ability to compensate and take out those distortions and produce images on the ground that are just as sharp as they would be if the telescope was up in space. I like to describe this as kind of the optical equivalent of your noise-canceling headphones. And the way your noise-canceling headphones work, as you know, is they measure the signal you don't want, which is the noise, and then they put that onto a deformable diaphragm, speaker, but exactly out of phase with the noise. The two signals combine and cancel, and you're just left with the signal that you want. So what we do in adaptive optics is we use a star or sometimes a laser beacon that we've projected to measure the distortions introduced by the atmosphere, and then we put that exact same shape into a deformable mirror rather than into a loudspeaker, and set it exactly out of phase so it simply cancels all those distortions, corrects the wavefront to what it was before it entered the atmosphere, and voila, you get an image that's just as sharp as you were in space. The challenge is you have to do this about 500 to 1,000 times a second, and you have to make those adjustments to the accuracy of a fraction of wavelength of light rather than a fraction of a wavelength of sound. So it's a challenging problem, but people are now doing it regularly. And it's the key to the power of the GMT and the other big telescopes is they now can realize their full theoretical potential, and you win as a huge power of the aperture then. So that's what makes this all so exciting.
Well, I was just going to follow up, Pat, with you said adaptive optics to handle what's going on in the atmosphere and being able to adjust for that, kind of like noise-canceling headphones, okay. But what about what's going on in the Earth below? Earthquakes, gravity, atmospheric pressure, ambient temperature, people walking by. I mean, there's such a fine tolerance here.
Mm-hmm. So the first thing we do is we build our telescope to make it extremely stiff. So when I was, I was about 9 or 10 years old and got my first telescope, one of the great frustrations is it kept wobbling all the time. It's very hard with a small amateur telescope to keep it from shaking, and it's no fun to look through a telescope where the image is wandering around because the telescope shakes. So we build our telescope to be very robust. We make sure that it doesn't shake in the wind, and then we put a dome around it to protect it a bit. But we can deal with most of those slow problems like slow atmospheric pressure variations, temperature variations, the sag that comes from gravity as you move the telescope across the sky. We have active systems that take those out. And the way we do it is we monitor the image of a star at all times, and we have an analysis tool that looks at the wavefront shape coming in from that star, and we recollimate and refocus the telescope every 30 seconds. So it's as if you have the autofocus on your camera. We just have that autofocus running all the time, and that takes out all the slow components, and then we have another system that does the adaptive optics that takes out the high-speed turbulence in the Earth's atmosphere.
And the adaptive optics, I'm going to guess, and this is an uneducated question, but often when you see photos of large telescopes, you'll see a laser beam being shot out, and I presume that is part of the optic adjustment system?
Exactly. So the way we did adaptive optics in the early days is we looked at a very bright star that came through the Earth's atmosphere with a high signal to noise that we could then measure its wavefront distortions, compare that to a perfectly flat wavefront, and make all these corrections. And you need a fair amount of data, a fair amount of light to do that, because I said you have to measure and make this adjustment every few hundredths of a second. So you need a pretty bright star to make that measurement. Well, the problem is you can only correct for angles that are very close to the reference source that you're using to measure the wavefront, whether that's a bright star or something else. So in the beginning, adaptive optics was limited to just looking around relatively nearby and bright stars, which meant only about 1% of the sky was accessible with that high angular resolution. Someone, and I have to admit, I don't know who, came up with the clever idea that we could take a laser beam, and if you tuned it to just the right frequency, it would bounce off of sodium atoms in the upper layers of the atmosphere, in the mesosphere at about 90 kilometers, and some of that light would reflect back down. And in essence, you make kind of an artificial star that's at the very top end of the atmosphere, and you can put it anywhere you want and use that to measure the wavefront system. So we create our artificial stars anywhere in the sky, so we'll get that beautiful high-resolution images wherever we want them, whether it's to look at a black hole or look at a galaxy or look at some other system. So that's where you see the laser beams coming from. The nice thing about the exoplanet problem, though, if we want to do adaptive optics and tune it up on a planet, the star itself is usually a good enough source to provide that correction. So we have the planet problem kind of solved with the star that they're orbiting. It's the galaxies, the black holes, the other things. That's what we need a laser beam for.
Yep, that makes a lot of sense. Now, is there anything specific about the choice of Chile for the location?
There's a couple of things. When you think about where you want to be on the Earth to do astronomy, first thing is you want to be someplace that it's dark, because light pollution just is not a good thing. It dilutes the light from the stars. It just adds noise. It's a real distraction. You want to be above as much of the Earth's atmosphere as you can practically be, simply because water and CO2 and aerosols, they absorb the light, they scatter the light. It's generally the atmosphere is not your friend in astronomy. But it's also critical that you want to be in a place where the airflow is very smooth, because while we've talked about adaptive optics and taking out this turbulence, we can't do it perfectly, and you want to start from as sharp an image as you can. And adaptive optics, while it's great, is really limited to infrared wavelengths and doesn't work in the wavelengths that your eye can see, or even the short ultraviolet, that's just a little shortward of what your eye can see. So we try to find places on the Earth that are dark, that have obviously good weather, because there's no point in going someplace cloudy, that are reasonably high, and most importantly, I think, that have this very smooth airflow. So when you put all those together, you wind up with two types of places on the planet. The first are isolated volcanic islands like Hawaii or the Canary Islands off the northeast coast of Africa, or coastal mountain range in which the prevailing weather has flown for thousands of miles before you encounter the mountain range. California is a great place for all of those things except for light pollution. So Los Angeles would be a nice place to build a big telescope, and they were built here in the previous century, but there's just too much light pollution. So Chile, it turns out, has all of these particular characteristics. It's extremely dry, one of the driest places on Earth. There's no light pollution because in the coastal mountain ranges away from the few big cities, there's just very few people because it's too dry to live there. The mountains get pretty high, but not so high that it's impossible to work. And the atmosphere, the wind just flows over the Pacific Ocean for 4,000 miles before it encounters the mountains. So the airflow is very smooth. It's what we call a laminar flow. So it makes images that are very sharp. So for this reason, most of the big telescope projects in the world now are in the Andes, and Chile's becoming a world leader in astronomy simply because it's probably the best place on the Earth to look up at the sky.
Antarctica has a lot of those characteristics, but it's so cold, it'd be too much of a pain to operate a telescope.
It has some practical challenges. So people are doing astronomy in the Antarctic. They're doing it only in the case where the conditions are so special for their science that it's worth all the extra effort. So it's difficult, it's more expensive, you have problems of frost, you have problems of accessibility, and if you're working on traditional optical astronomy, you have the northern or southern lights, which are beautiful, but they add a lot of of extra signal and noise and things that you really don't want. So I think for most astronomy, Hawaii and Chile are the best places to be. If you want to go to long wavelengths, the Antarctic is great, but boy, it's hard and expensive, and you really need to go there in order to make it worthwhile.
Now, Pat, the GMT is described as the first of a new class of extremely large telescopes. So what would the specific definition be for a telescope that is classified as extremely large?
Well, this is one of those funny bits of nomenclature, and it came from the Europeans to begin with, because they had built some telescopes in the 1990s and early 2000s that are 8 meters in diameter. And there's a number of 8 to 10 meter diameter telescopes around the world. There's 2 10 meters in Hawaii. There's an 8 meter in Hawaii. There's some 8 meter telescopes in Chile. But the European Southern Observatory, they were very clever, and they said, we'll call this the Very Large Telescope. Okay, well, very large. So when you start designing the next telescope, what do you call it? Well, you can call it extremely large, just because that's bigger than very large.
Yeah.
So that's how we got there. It's not a very clever name. The radio astronomers built a telescope in New Mexico, and they called it the Very Large Array. So what do you do next? I don't know. But in practice, we think of the extremely large telescopes as they are a qualitative gain over the 8 to 10 meter telescopes that we have now. And what we've learned over history, if you go back again to Galileo, is that roughly every 30 or 40 years, someone builds what is then the largest telescope on the planet, and typically they're a factor of 2 larger in diameter than any telescope that's preceded them. And that factor of 2 turned out to be a pretty interesting number. First of all, going a factor of 2 in diameter for an optical system is technically very challenging. The cost goes up at a rate that's faster than the square of the aperture, so they get very expensive very quickly as you get larger. And what's turned out is that the scientific benefit has always turned out to be larger than the simple factor of 4 you think you would get just by the collecting area that goes like the square of the telescope aperture. So when I look at this over sort of 400-year history, my view is if you can go between a factor of 2 and 3, that's about as hard as a problem as you can take on and hope to succeed. It's about as much as you think you can afford, and the scientific benefits are huge. So we view GMT as the next logical doubling or tripling in size, just as the 100-inch telescope at Mount Wilson was a doubling, the 200-inch at Palomar was a doubling, the 10-meter in Hawaii was a doubling. The GMT is a factor of 2 to 3 larger than any telescope on the Earth. That's why I think it puts it into an interesting class.
So really, it's incredibly difficult, but it's always proven to be more than worth the effort.
Absolutely. Always been more than worth the effort, and only once can we point to a ground-based effort where a team tried to build the next biggest telescope in the world and didn't really succeed. And that shows you that it's hard, but not too hard.
Sure. So the extremely large telescopes, they don't function like, my telescope that I use in my backyard. It's a completely different type of light collection method, right? Can you sort of walk us through how they collect the light? Sure.
There are essentially 2 classes of telescopes. They're the ones that involve lenses, which is where Galileo started. The people who made the first telescopes, they were Dutch and Italians and Germans. They had learned to be spectacle makers, and people realized if you took 2 lenses and lined them up, you could see things magnified from great distances. So for a long time, telescopes were based on lenses, what we call transmissive optics, where the light goes through the optic. That has a lot of benefits. It has some drawbacks, and one of the drawbacks is as you make the lenses larger and larger, they have to get thicker. That means they absorb some of the light. It means the demands on the material are very demanding because you have to get glass that's very pure and very clear. And it turns out, for technical reasons, you have to mix different kinds of glass together if you want to get a sharp image. And what happened around 1880, 1890, people were reaching the limit of these refracting telescopes. The very long tubes, you've seen some of the classic pictures of these really long telescopes. And most small amateur telescopes, like the ones I had as a kid when I first started out, were these refracting telescopes. Now, Isaac Newton came along and had a very clever idea. He understood optics, and he said, if you can bounce the light off of a mirror, but make the mirror curved, you will bring it to a focus. And he made the first reflecting telescope. And at the time, that was thought, wow, that's a clever idea. But it really didn't take off for a couple of 100 years, primarily because the early reflecting telescopes used mirrors that were made out of metal. And the problem with metal is it tarnishes, so it loses its reflectivity, and it tends to change shape as a function of temperature, so the telescopes were not very stable. The big breakthrough came in the 1800s when people realized you could make a reflective surface out of glass. Glass has all kinds of amazing properties, but one thing it doesn't have is it's not very reflective. But you could make a mirror out of glass and then coat it with a thin film of metal. And that's what's led to the current generation of reflecting telescopes. And every large telescope, whether you're an active amateur or building astronomical, professional telescopes, they're all reflecting telescopes based on mirrors. Now, the big change, though, that happened in the 1990s that made it possible to make 8-meter telescopes and now the ELTs is, unlike the telescope you have in your backyard, these are all active systems. As I mentioned earlier, we measure the light from a star every 30 seconds. We continually recollimate and refocus the telescope because the mirrors tend to change shape from gravity, they change shape from temperature, and if you didn't actively control them, they would just make images that are pretty soft after a relatively short period of time. So it's bringing the power of computers to the glass, to the metal on the glass, that makes all of this possible.
Now, can you describe the mirror array itself? I know there's 7 big mirrors, and then there's a secondary set of mirrors, and I believe there's like a final mirror, and then it gets reflected into a CCD?
Right, pretty much. So what we really would like to do, if we could, was just make one really giant mirror. But we think there are technical reasons why that's pretty impractical. First of all, when you make a mirror that's very, very large, it takes a long time for the glass to cool as you melt it, because you can't have it melt or freeze at different rates. You build in stresses in the glass that will lead it to crack or to have the wrong shape. And say even if we could make a 25-meter mirror in a laboratory somewhere in the U.S., how do you get it to the top of the mountain? You just wind up with practical difficulties. So people have concluded that somewhere between 8 and 9 meters is the maximum size of an individual mirror. So then the question is, well, how do you make a telescope that's larger? And clearly what you have to do is combine the light from different mirrors into a single focus. There's different projects around the world approaching this different ways. One approach is, well, you make a lot of really small mirrors and you fit them together very closely and you just make a lot of small parts and build a big mirror that way. We think that the mirrors that we can make in Arizona are the best mirrors on the planet. We think there's advantage to having as much of the mirror in a single smooth piece of glass with no edges as we can is the right way to go. So what we do is we make these 7 mirrors, but it's not as if you just took 7 telescopes and put them all on the same structure and kind of pointed them in the same part of the sky. Rather, what we do is we take a single optical shape and we make individual elements that when we combine them make that parent optical surface. So the way I think about it is if you took a salad bowl, say, and you just cut out circles with a biscuit cutter around the periphery, they would have this funny asymmetric off-axis shape. That's what the GMT mirrors have, so that when we put them in the telescope mount, they form the shape of a single 25-meter mirror, but composed of 7 pieces, each of which are 8.5 meters in diameter. So then the light comes down from the stars or the planets. It hits these 7 mirrors. They bring the light back up to a focus, but rather than trying to put a camera at that focus, which would be very difficult, we bring the light back down. And we realized early on that the simplest control problem would be to have the light from each of the primary segments, the big mirrors, go to a small mirror, in this case about a 1-meter diameter mirror. So the secondary mirror array is just a very small version of the primary mirror array, and that then reflects light down through a hole in the center segment of the primary mirror array, where it can either go directly into a camera with a CCD or can be reflected at a 45-degree angle to smaller instruments to do particularly specialized measurements. So it's what we call a doubly segmented optical system, and it provides us a way to control all the mechanical issues we talked about and yet build this big aperture, but in parts that are manageable sizes.
And again, the asymmetry of the mirrors that you mentioned, kind of given the salad bowl illustration, it's because they're all working together as if they were one large mirror, but in fact they are several different ones.
Exactly. And it turns out that asymmetry is the hard part of actually making the mirrors. And that's where we had to spend a fair amount of time and effort learning how to make those off-axis mirrors, because they're pretty far from the nearest axisymmetric shape. And in optics, the difficulty of surface is described by how far away it is from the best fitting sphere, because a sphere is a relatively easy thing to polish because it has the highest degree of symmetry. A classic optical mirror for a telescope is a shape as a parabola, and parabolas are not that far from spheres. And so we typically measure how far is it from the nearest sphere in the number of wavelengths of light. And so something that's 10 wavelengths or 50 wavelengths, those are hard optics. The GMT is 50,000 wavelengths away from the best fitting sphere. It's 14 millimeters difference from edge to edge as you go around the mirror. So polishing that shape that's 50,000 wavelengths away from a sphere, but to an accuracy of 1/20th of a wavelength, that turns out is a hard problem. But we've learned how to do it.
I can only imagine.
Well, I think some other, there's the 30-meter telescope, there's the European Extremely Large Telescope, and my understanding is they were designed with hundreds of smaller mirrors rather than taking on the 7 massive mirror problem that you guys took on. So, I mean, do you really feel it's worth the trouble as opposed to the smaller mirror solution that these other 2 projects have gone for?
Indeed, we do. And one of the major differences is we had one problem to solve, which is how do you polish that off-axis mirror? Because of our 7-mirror system, the 6 outer mirrors are identical. So once we learn how to make one, all the others are the same. Now, for, say, the 30-meter telescope or the European ELT, they have a great technical approach, but of their many different small mirrors, they are many, many different optical shapes. So I believe the 30-meter telescope has 85 or 84 different optical prescriptions, and the Europeans have about 125 different optical shapes, so they have to have an optical test for each one of those families of mirrors. It's not an insurmountable problem. They know how to do it. You have to make a lot of test optics. You have to really work on the problem of how do you make those mirrors work as a system, whereas our biggest challenge was in the laboratory and the initial fabrication, and we've solved that problem. So it's really a question of how you want to trade which problem you solve. One big problem or many smaller problems and a control problem. I'm confident that both approaches will work. It's just a question of which particular path you choose to go down, and we're quite happy with the path that we've chosen. And it's nothing, like success that we've shown we can make the first mirror, and we're working hard on mirrors number 2, 3, and 4 now, and we've got all the materials for 5 and 6 stacked up, and we're going to buy the glass for mirror number 7, and so we're well on our way along this problem.
Can the system be upgraded over time, for instance, with a better CCD or, some other components as new technologies come along? Is it modular?
Absolutely, and this is one of the key advantages to having a telescope on the ground as opposed to in space. Typically, when you launch a space vehicle, a satellite, an experiment, you launch it and it's gone. You never get to go back up and fix it. The Hubble was the exception in that people could go to the Hubble because it was in low Earth orbit, and they could change out the scientific instruments, they could change out the data recorders, they could even change the batteries. On the ground, we can change essentially anything we want. The things that you typically don't change are the primary mirror optics, but all of the cameras, the wavefront sensors, the data systems, we renew those regularly on somewhere between a 5 and 10 year time scale. And the key is, as you say, is the technology evolves, and the last thing you want to do is lock yourself into yesterday's technology while you're building tomorrow's instrument. So we want to make sure that we can swap out any subsystem on the telescope, except the primary mirrors, at any time. So we have a budget to renew the scientific instruments. We will spend roughly $10 million a year building new instruments, and we have a budget to update the adaptive optics. Because one thing that we can be sure of is that people will come along with better algorithms, better optomechanical systems to take care of this adaptive optics problem, and we want to be able to swap those out on a reasonable time scale at a reasonable cost.
Now, as a kid, I got Astronomy Magazine. I had a telescope for some amount of time, and boy, the magazine was an inspiration because you get these fantastic pictures of nebula and galaxies and different stars and so on. But aside from that visible spectrum that is so impressive to us humans and inspiring, are there other things that the GMT is going to be able to see?
Yes, well, I had a similar experience that as a kid, seeing the astronomy magazines and the books with all these beautiful color pictures were what inspired me. But as you study physics and astronomy, we learn that most of the scientific information we get comes from the spectroscopy, and it comes from measuring the signatures of different atomic species, different ionization states of atoms, and using them as diagnostics for physical conditions, for temperature, density, motion. So most of what we do as astronomers now is we don't take pictures, we measure spectra, and often we measure spectra in parts of the electromagnetic spectrum that your eye cannot see, that don't lend themselves necessarily to the beautiful pictures, but it's become a science of precision measurement, of detailed, in some sense, kind of physical chemistry and physics of the environments, whether it's interstellar matter, stars themselves, planetary atmospheres, or the dynamics around really exciting and violent objects like black holes, exploding supernovae, gamma ray bursts, and so on. So it's an extremely rich field, both from a phenomenological point of view and then from the tools and techniques that we can bring to bear that are so far beyond simply taking pictures that it's a much, much richer toolkit that we have now than astronomers had, say, 100 years ago, when really they had photographic plates that could record images, and that's all they had.
So apart from, or in addition to the mirrors and the CCD and all that, I presume there's other scientific instrumentation there that will be used to analyze these other wavelengths and things like this.
Absolutely. And so we often find that the challenge in ensuring that a big telescope can be used to its full scientific potential is limited by our ability to make the small optics. And typically it's the optics that disperse the light into its constituent colors. That's often the biggest challenge. So Newton first did this with a prism and understood that white light could be dispersed into the rainbow of colors and then recombined back to make white light. Prisms are limited in their ability to disperse the light very much, and they have some other properties that are not ideal. And we use what we call diffraction gratings, which are rulings that are grooves, in essence, in mirrors or transmissive optics that allow us to interfere different parts of the light against each other, and that's how we disperse the light and measure the spectrum. But those are very high precision optics, and ideally, as you make your telescope larger, everything gets bigger. So your camera lenses get bigger, your gratings get bigger, your prisms get bigger, and you run into the problem where you start to reach the limit of the materials that you can manufacture and your ability to control them with the precision that you need. So a lot of the thinking we've been doing on GMT is with the instrument teams at our partner universities to come up with clever schemes that we can use today's technology or moderate leaps in that technology that allow us to build instruments on telescopes 3 times larger than we've done before, but yet using the same basic materials we have today. So that's, from a technology point of view, you think of what's challenging about the ELTs, it's adaptive optics, and it's making these specialized instruments that require a lot of high-tech work in detector development, optical controls, signal processing. That's where a lot of the really challenging work is going on.
Well, there's a lot. You mentioned mirrors. You mentioned all the scientific instruments that are going on. There's a lot that's happening to bring us to a point where we can actually use the telescope. How far away is that?
Well, in our case, we think we will have the telescope on the mountain and some of the mirrors ready to go in it in 2022 or 2023. We won't expect to have all of the optics on the mountaintop until 2024 or even 25. It turns out that building a telescope this size takes 20 years. And if they had told me that when we started, I might have thought a little differently. I was thinking it was going to take 10 years. But these days, in so much in life, if you want to have an impact that's beyond what's been done today, it's a decades-long plus investment. There's a few places we can see in the IT world in Silicon Valley where people have very short timescales to have a high impact. But in science, particularly in the physical sciences, we're really looking at decade-long kind of work.
Is it the glass that's taking so long, or?
Well, it's a combination of things. The glass is usually the pace-setting item. Making the optics is usually what takes the longest time. And in our case, our end date will likely be set by when the 7th mirror is delivered to the mountain. But part of what makes big science so challenging is you have to solve several problems in parallel. So you have to come up with a good idea. You have to enlist people in that idea. So there's a lot of social engineering and collaboration that has to go on to get enough people to buy into that idea to make it work. There's a lot of detailed engineering and planning that goes on. So we don't get to the stage of cutting any metal till we really have all the plans worked out. And something this complicated takes a lot of planning. But the biggest challenge, I think, that we've all found is bringing together the financial backing and the financial management to do these billion-dollar scale scientific projects is very hard, and it takes a long time. And I think when we look back at the GMT or we look at the ELT when it's done or the 30-meter telescope, people will say the thing that set the pacing item in the end was getting all the funding in place. And that's turned out that that's been our similar challenge. We're in a good place now, but it just took a long time to build the partnership, to build the trust, to make the case, to get people to commit the funds. And, that's the way it should be. One shouldn't commit that kind of money overnight. You have to really do your homework. You have to do all your planning, and that just takes time.
It's certainly no cheap undertaking, yeah. And that leads into actually the next question that I had for you was, where does the money for this come from? Is it, governments? Is it private endowments? How do you go about raising the kind of funds that you need for a project of this scale?
Well, there's different ways one can approach this, but we have approached it from a very diverse point of view of trying to bring together a lot of different funding streams. We started this as a group of academics, people working in universities and small scientific institutes, and we wanted to keep the essential spirit of a university-led project. We didn't want to just sort of jump right into the government-funded big science approach. And so we built up a consortium of 11 research institutes. Each of them has committed their share of the funding. And in some case, say for our international partners, that comes from their federal governments in some cases. In some cases, it actually comes from state funding agencies. Our U.S. universities, some of them are using funds that they have in their own research and infrastructure budgets. Others are funding them primarily from philanthropy. And some are doing some creative financing where they can borrow some money on long term and rebuild that out of fundraising and other financial development processes. So like any big project, you have to build a funding stream that draws upon different elements. In our case, we've tried to keep those elements in the academic world to the degree that we can, whereas the European project is really funded by European governments through a common framework in the EU. Turns out that is challenging as well. And the 30-meter telescope has yet a different sort of hybrid approach to ours. So ours, as I say, it's diverse, but it's primarily philanthropically driven in the U.S. With some institutional backing from our international partners.
Now, this is the construction phase we're in now that is driving the need for a lot of this money. When the GMT is up and running, will the funding situation change?
Well, it changes in character in that it becomes an ongoing operational challenge, but the partners who participate in the construction fully understand the long-term commitment that's required to operate and keep the observatory at the cutting edge, and their financial planning then includes this ongoing operations budget. And the rule of thumb is somewhere around 5% of the construction cost needs to be allocated on an annual basis to operate and maintain the facility. And our partners understand that. We have a budget for that. We have a staffing plan that calls for about 125 full-time employees working basically around the clock, because an observatory never sleeps, to make sure that we're doing science at night and we're doing maintenance during the day. And we're always looking ahead to keep the technology up to date and keeping the basic infrastructure in place and maintaining the roads and the power and the water and the things you take for granted until they stop working. And the last thing we want to do is not be able to do science at night because we just didn't do our basic infrastructure upkeep during the day. So it's a different challenge, yet it's one that our university partners in particular are well suited to addressing, because universities live forever. They have annual operating budgets. They understand what long-term commitments mean. And so this is something that doesn't frighten us.
Sure. Now, is there still room for other institutions to get involved in the GMT?
Sure. There is, in a variety of ways. There are still a number of key technical decisions and developments that have to be made. There's science planning that goes on, and there is room for additional partners who want to participate in construction or operations or both, and then have privileged access to the telescope at night. So while we have a good partnership here in the U.S. and in the Asia-Pacific region, our partners are welcoming of other universities and institutes of similar standing. So there's a few institutions who I won't name that we'd love to have as partners, and we are actively both discussing with them, but want to let the world know that we are welcoming further participation.
Well, Pat, last question for you. We appreciate you taking the time with Citizens of Tech today. In your opinion, are we alone?
As a scientist, I try not to have an opinion, but if I made a hypothesis, I would say the odds of us being alone are negligible. So we now know how many planets there are in the observable universe, in what we call the Hubble volume, the part of the universe that we could in principle observe. And that is somewhere between 10 to the 20th to 22nd power. That is 10 with 20 zeros or 22 zeros after it. So if we are alone, we are only 1 out of 10 to the 22 planets in the universe that has life. That seems unlikely to me. As a scientist, things that just don't happen that are that rare. So I'm confident that we're not alone. The real question is, will we ever be able to prove that we're not alone? And that's a daunting problem. That's a challenge just because the universe is so big, the spaces and distances are so vast. But I find it personally one of the more comforting things to know that while the Earth is evolving and we're kind of messing up here and there in various places, there are other places in the universe where life is going on and it's very diverse, and there's just much more out there than just us. And I just find that a comforting feeling.
Thank you once again for joining us, Dr. Patrick McCarthy from the Giant Magellan Telescope Project. And we hope you learned something today on Citizens of Tech. If you like what we're doing, please share this podcast with your friends, rate us on iTunes, send us some upvotes in the Citizens of Tech subreddit. Until we show up in your podcatcher again, visit citizensoftech.com where you can become a Patreon patron. Now, go outside and tilt your head up and stare at the stars, unless there's only one really bright one in the sky. In that case, maybe you should avert your gaze.